Hey, Mars, can you hear us?
Yep.
You might have to yell for people to hear you.
Okay.
How's Germany, Mars?
Pretty good. Weather is as bad as in Seattle though. So
Rough. Rough going. Actually, Seattle is beautiful today. You're missing out, man.
yeah. Let's hope it stays this way.
Yeah. Alrighty, let's get started. So, welcome to CSE 478. We call it autonomous robotics, cars, whatever you want to call it, but we're gonna be learning how to program that race car. So, I'm your instructor, Abhishek. We have 4 TAs and we'll introduce them later in the class today. So, sorry. Okay, I'm recording on Zoom. Hopefully that's okay with everyone because we can just have lectures online. So if you miss, you can just go online. We should have all slides and lectures online. So if you're not able to attend any day, it's fine. Just go online. Everything should be there. All right. So what is CSE 478 about? Right. What we're going to do this quarter is we're going to be programming race cars. Right? So we're going to be programming these cars, which we call the Musher cars, which is the multi-agent system for non-holonomic racing. So this is a card that we developed here at UW, and it's these small race cars which are less than $1,000 each, and they were developed over many iterations by some folks here in the robotics group. And their goal is to help with education and research and driving extremely fast around the building. So that's the first iteration of the race car. And then, it was developed to be better and better. And now you have the best possible version. And so extra credit for anyone who improves on the race car. So if you want to put an arm on it, one letter grade up. But what I learned yesterday is that mushing is a sport where dogs pull sleds, and so that's the origin of the name. And because we're huskies, apparently we call the cars mushers. But really, they're a platform for doing research on multiple agents, trying to do multi-agent coordination, trying to do high-speed driving, trying to do navigation and planning and control. And so lots of folks use versions of these for research or things that are related to research. So what you guys are doing is actually very close to what people actually do for research. So that I've never seen a class like this. So exciting times for all of you. So let's look at the race car and see, what the system's all about. Right. So it starts with it's like a somewhat standard race car. It's inspired from this MIT race car, but you have like a racing chassis, and then you have a bunch of, it's like a modified standard RC car with a LiDAR and a bunch of cameras and a bunch of higher speed servos, right? So you have a chassis, you have extra high power batteries, you have a bumper switch to detect when you bump into things. You have a real sense camera, which is a depth camera, so you get RGB and depth from there. We're not going to be using that this quarter, but it's nice to have. If you want to use it, let it grade up. Sounds great. Then we have a 2D LiDAR, which does laser scans, tries to detect how far things are. Right? And then we have a nice NVIDIA Jetson, which is the computer that powers it. Right? And so overall, it's like a very capable car. You can power lots of stuff. It can go pretty fast. Our TAs have done lots of cool research with it. So bother them, they know much more than me. All right. So here's some examples of the car in action. So this is what you can expect to be able to do by the end of the quarter. Let's see. There we go. So this is from a previous quarter, driving around the Allen building. So this is like one of the first iterations of the car, but basically running the stack that you guys are going to be developing this quarter. You're trying to navigate around the building, trying to follow a series of waypoints around the building while avoiding obstacles that might arise in the process. And so you can see here a visualization of the planning. So red is high cost, blue is low cost. After forgiveness, it'll be fine. And so we're going to learn how to, develop cars like this and develop navigation techniques like that. All right. This. So, okay, so that's kind of a video of what you're hoping to accomplish. But what are we hoping to learn, right? So we don't want to just make fancy demos. We want to learn, techniques that are generalizable and useful beyond race cars, right? And who cares about an RC car? You want to develop self-driving cars and humanoid robots and so on, right? And so the goals of this course are really to, enable us to learn the algorithms for autonomous driving, implement them on a race car, and then try to figure out how these connect to broader applications beyond the race car. Right? So we don't just care about race cars. We want to use the race car as a learning platform to learn about self-driving cars or robot arms or humanoid robots. A lot of them use the same techniques. And so what we want to do is we want to learn a small set of fundamental tools, right? So we want to learn tools which look like, sorry, my clicker is misbehaving. Bayesian filtering, which is our first set of techniques we're going to learn. We're going to learn techniques like model predictive control. We're going to learn techniques like roadmap search, probabilistic search, and all of these are going to help us power applications, which are, pretty impressive, like flying drones at high speed, or flying a helicopter upside down, or self-driving cars, and so on. Right? So it's like pretty much somewhat small improvements on top of these fundamental techniques that are powering a lot of the robots of today. And so hopefully through an understanding of these techniques, you guys will be able to develop robots of your own. And so we'll go over some of the learning objectives and logistics, and then I'll show you guys a bunch of cool robot videos. Right? Any questions so far? Any concerns? Yeah? All right. So are we going to learn about all types of robotics in this course? No, we're just going to be learning about mobile robots. But mobile robots are certainly not the only type of robot in the world, right? So a lot of what you see are robot manipulators. So things like robot arms, multi-fingered hands, things like that are robot manipulators, which are trying to manipulate the world. And so things that, move objects, do things in the household, Rosie from the Jetsons, right? All of these are, I guess that's too old for a lot of people. Yikes. But a lot of these are robot manipulators, and a lot of my research is on robot manipulation. So if you want to talk about robot manipulation, come by my office hours, a lot to discuss. We also have humanoid robots, which are bipedal walking robots with hands, things like the Tesla Optimus Pod or the robots from Boston Dynamics. And we're not going to be covering those this quarter, but a lot of those are also built on similar techniques. And then we have an interesting class of soft robots. These are robots that are like fish and tentacles and octopuses and underwater and snakes and so on, which are interesting because they're really hard to model, right? So if you have like flexible material which is changing shape all the time, it's very hard to model, and so it's very hard to control. And so some of the techniques that we'll talk about at the end of this class are useful for learning how to control soft robots. And Karthikeya is working on a soft robot right now, so he can educate us on that as well. All right, so to study mobile robots, what are the techniques we're going to learn, right? So the first thing we're going to learn is localization. You guys can see it, right? So localization is essentially where you are in the world, right? So you want to localize yourself, and you want to figure out where you are in the world under uncertainty, under occlusions, under unexpected disturbances, right? And so the first thing we'll study is localization. The second thing we're going to study is planning, right? So planning is figuring out how to set a series of goals to accomplish, what you want to accomplish. Let's say you want to go from here to Gates. How do you set a series of waypoints that successfully accomplishes the path of going from here to Gates without hitting anything, right? So planning is often long horizon search, right? So you try to figure out where to go. And then we're going to have a series of topics covering control, right? And so control is similar to planning, but control is saying, once you've decided the path you're going to take, how do you navigate that path while dealing with disturbances on the way, right? So like the friction of the car might change. Someone might introduce a small disturbance. There might be wind, there might be friction, right? And you want your system to be able to deal with noise and be able to reliably and safely operate under that noise, right? So that's what we're going to cover under control. And then lastly, the topic that I like the most is reinforcement learning, right? So we're going to learn how to, control these systems through trial and error. Let's say your system is not perfect. You're deploying it in a new scenario. How do you use experience to get these systems to be better and better, right? So the first three techniques that we're going to talk about are model-based techniques, right? So you assume a known model of the world, and reinforcement learning is a model-free technique. So you're trying to use data in the world, try to use machine learning methods to figure out how to control these robots in new environments for new tasks, right? And so that's what a lot of our research is on, and we have an exciting section on that at the end, right? But the thing to note about reinforcement learning is that it absolutely doesn't work. So don't use it on your robots. But it's on the way to work. So there's still hope. But I think it's an interesting set of things to cover. Things we're not going to be covering as much in this class are mapping, right? So a lot of times robots are used to build maps of the world. Like you're trying to map a disaster site, you're trying to map a construction site. You're trying to figure out, what's inside a building which has nuclear radiation. A lot of that is mapping, right? And you want to do mapping under uncertainty. And so things are changing in the world. You don't exactly know where you are, and you want to figure out how to do mapping. We'll touch on that, but we're not going to cover it in a lot of detail. And a lot of stuff we're going to do is assuming that the map of the world is known, right? Then we know the map of the world, how do we deal with it? But there's an interesting line of work on how do you both map the world and figure out where you are together, right? Which is called SLAM, and we'll cover a bit of that as we go along. We're not really going to cover computer vision that much, right? So there's a huge field of computer vision. How do you take images or depth images or things like that and try to make sense of the world, right? So where are objects, what are objects, segmentation. We're not going to really cover those things, although a lot of them are extremely important, right? And lastly, we're not really going to cover robot and actuator design. We're going to take this race car as the gold standard. But if any of you want to build a better robot, you're more than welcome. But there's a lot of really interesting work on that. I'd encourage you to take Josh Smith's class. He teaches lots of cool stuff about that. All right, so what we're going to try and cover in this class is a combination of localization, planning, control, and reinforcement learning, right? 4 objectives, very simple. So putting it in the context of this race car, right? The first thing we want to do is we want to do localization, which is estimate state, right? Which is say, let's say you're in this hallway, right? There's noise in the world. There's no like GPS tracker in your building. You need to figure out where you are. And so localization is basically trying to use sensor readings from the world to figure out where exactly you are, right? So you're trying to localize your system. And so that's our first learning objective. The first 3 weeks or so of the class is going to be on localization, estimating state, right? And these techniques are going to be really useful, not just in localization, but also in further things. We'll see how they're all connected, right? The second thing we're going to think about is how to plan a sequence of motion. So as I was saying, you want to figure out how to go from here to here, right? You want to figure out how to do it while avoiding the obstacles. Now, why is it not just a trivially simple problem? I mean, you just want to go from here to here, you can just go on this way and this way and this way. Like what makes it not trivial? Yeah. You can't fit in some of those places. Yeah, perfect. So there's obstacles and there's the dimension of the car and you can't fit in some of these places. Other thoughts? Yeah. Those things might be moving. These things might be moving. Yes. Perfect. So the map might be changing and you need to account for that. Another one. Yeah, good.
Are always complicated, sort of like a circle, like.
Yeah.
You never know in this.
Right. Right. So it's not a, the name of the car is Musher, which is multi-agent system for non-holonomic racing. So when non-holonomic, you can't just move arbitrary directions. You have to follow, you know, the curves that come from steering, right? And so the set of motions that you can actually accomplish is not the space of all possible motions. And so navigating that space is not trivial, right? And so you have to, in addition, you have to do this when you have velocity. You have to do this when you're dealing with physical constraints. So it's not trivial to figure out how to navigate themselves. And this gets even harder as you go to higher dimensional systems. You have a humanoid, it's 30-dimensional, and you have to figure out how to navigate through, you know, a cabinet. It's a very hard problem, right? And that's the problem of planning. The next thing we're going to figure out is how to do control, right? So control is saying, okay, where we figured out a set of waypoints, right? Let's say our path is this one, and we want to follow those set of waypoints. Why is that not trivial? Right? I mean, you've told it where to go. Where you go determines your velocity. Why is it not as simple as just executing that velocity? Right. Your robot might drift because there's unmodeled things in the environment. Things might be changing. There's noise. There's disturbances. Right. Your battery might deplete. There's lots of things that could happen. Any other thoughts? Trajectory planner doesn't work. Let's say one of the obstacles moves or you misestimated something, you have to like deal with it. And so what we're going to do in this section is we're going to deal with feedback control. So trying to use feedback from the environment in terms of sensor readings, in terms of images, things like that, to figure out how to correct your behavior. And so that's our third objective. So that's localization and state estimation. And so estimating where you are in the world, planning where to go to accomplish a particular goal. And then this is trying to deal with, you know, short horizon behavior, so that you deal with drift, deal with noise, deal with disturbances, right? Or deal with, you know, incorrect models of the world. Right. Now, beyond this, we'll touch very briefly on how to estimate maps, right? So what makes estimating maps different? Right? So you know, you're in the world, you have a laser. The laser is telling you where obstacles are. So what makes it hard for us to estimate maps? Because the lasers a laser basically shoots in different directions and tells you how far things are, right? And so shouldn't that just give you a map trivially? What makes it hard to estimate? Things could be in the way of each other. Yeah, so there's occlusion and partial observability. Yeah. Sharp corners, yeah, you can't really look around the corner unless you have particular types of sensors.
Depending on the resolution that you're at, it might take a lot.
Right, it could take a lot of time, and you're trying to do this at high speed in real time, and that's difficult, right? The other thing that we should note is because we don't have a GPS sensor on the robot, you actually don't know where the robot is, right? And so the problem of localization that we talked about last time assumes that you know the map, and the problem of mapping assumes you know where the robot is, and really you don't know anything. And so you want to do the problem of localization and mapping together, right? And so that's what makes it hard. And then we're gonna think about whether machine learning can help us resolve some of these issues, where it can be helpful. Generally, roboticists don't like to use a lot of machine learning for good measure because it is unreliable and hard to use. But these methods are getting a lot better, and I think it's worthwhile to study which of these could be useful for production systems. And lastly, we're going to try and learn how to program robot software, right? So robot software is not just standard Python. There's a bunch of communication. You're interfacing with embedded systems. And there's a whole operating system called ROS, Robot Operating System. And we're going to try and learn how to use that and try to develop all our software. So we're going to learn how to write good robot code, test it on hardware, test it in sim. So because I'm a junior professor, this is actually my first class for undergrads. So good luck to all of you. But we can play fast and loose, and we can do other things. So if there's other things that you all want to cover, we can make lectures for those. So are there things that come to mind that I didn't cover here that would be really exciting for us to cover? Yeah.
You ever worked on a project before, like,
Have I worked on this project?
like, what's an interesting project?
Oh, I work on a lot of robot manipulation. So I work on a lot of how do you have reinforcement learning methods try to like do tasks in the home. So for instance, one of the problems we worked on was trying to use a robot hand to assemble objects. And so the robot hand is high dimensional. You have to deal with contacts. You have to deal with like fine grained motion to do tool use. And so we've tried to use reinforcement learning algorithms to do like tool use on a real hand. And so that's one of the ones we cover. It was exciting. We've been working on some learning from video. So trying to use videos of humans to bootstrap robot learning. That's been fun. Trying to learn from human feedback. So you take a robot, connect it to the web, have people give it feedback, then try to get it to improve over time. Yeah, a bunch of things like that. But a lot of my research is really focused on it. So how do we build machine learning algorithms that can learn in the real world around people, from people, and in ways that are efficient enough to be practical. Right. So yeah, I'll show you guys some of my research as we go further along, but that's really where the focus. Cool. So here's some videos of methods that use these techniques. So
Drones came onto the scene 4 or 5 years ago, and I think they really captured people's imagination with all the incredible concepts that are out there. There's this general.
There's one from Skydio, which is a drone company, and they largely work on photography, right? So they like try to follow you when you're doing adventure sports, and they try to do like high-speed trail following and things like that, and deal with you disappear under snow or behind a tree or something. How do you do person following at high speed indoor? And so they actually started with a fixed wing aircraft. So they have this like huge aircraft flying inside a garage at high speed. And from there they went to like drones, which are high speed and indoors. And a lot of them are using the same localization, planning, control techniques to deal with the inherent noise that comes with dealing at these high speeds. I think Skydio might have gone bankrupt. Maybe not. Not sure. But I think they do really cool work. Because they're dealing with all of these unstructured terrains. You don't have perfect maps of these. You have some maps of these, but how do you deal with the inherent noise in the system? And this is one from UW, from Byron Boots and friends. So they actually have a ranch, maybe an hour or so outside of the city, and they try to do high-speed off-road driving, using a lot of basically these techniques, right? So they're trying to like drive through lots of hills and lots of bushes and lots of ditches and The updated video, which I'll try to get for you all, they're flying over cliffs and stuff. It's super cool. And if you ask Baron nicely, he might let you go ride in one of them. But yeah, so a lot of these are basically trying to do, it's like a large race car. They're trying to drive quickly through, lots of occluded terrain that is not so trivial to drive around like a building, right? You're going through puddles and your vision is occluded, and a lot of these techniques we talked about are super important here. Right, so hopefully some of you will be inspired to, build robots like this soon. Alrighty, and last objective I wanted to cover is learning how to read and analyze research papers. Right? So robotics and machine learning is going super, super fast. So this is a graph of the number of papers that are being published on arXiv, which is like an online paper repository per year. And you can see that it's just blowing up. Every day there's like 600 papers on arXiv. And a lot of them are good, a lot of them are bad. And so the hope is that we can help you understand what papers are good, what papers are bad, how to read papers critically, and ask the right questions to do your own research. So that's kind of the last objective here. And we're gonna have paper readings and guided discussions to help you understand how to do that. Cool. Any questions or comments on what we just covered? Does it seem exciting? Does it seem boring? Seems all right. Cool. So let's cover some logistics, right? So we're gonna have it here, 1:30 to 2:20. I typically run overtime, so hopefully I don't get in trouble. I'm the instructor. I'm an assistant professor in computer science. And we have 4 awesome TAs who will introduce themselves in a second. So a little bit about myself. I'm somewhat new. This is my second year teaching at UW. Prior to this, I was in Oregon. I was born in Oregon, and I went to India, got the accent. And then spent the last 10 years in Berkeley. And then I did my undergrad and grad school at Berkeley. And spent a year at MIT doing a postdoc, and now I'm here. So yeah, West Coast, Best Coast. And things I'm interested in are reinforcement learning, applications to robotics, things like optimization and control, and more generally, I'm interested in machine learning topics like robustness and generalization. Right? So I'm really a machine learning person who moonlights as a roboticist. So if you're interested in robotics or machine learning, come talk to me. I'm happy to chat about anything in my office hours. So yeah. All right. So Marius, do you want to introduce yourself? Marius is on,
Yeah.
but hopefully you guys can hear him if you're super quiet. Go ahead, Marius.
Hey, my name is Marius. I'm on Zoom because I'm visiting Germany right now. So it's almost the end of the day here, but you guys still have a lot ahead of you. Yeah, I'm a second-year PhD student. I'm advised by Dieter and Abhishek. And I'm like broadly interested in robot learning from sim and from real data. I think both can like kind of benefit from each other. I'm also interested in computer vision. That's not on here because I've been dealing a lot with like a bunch of robot things. So I didn't have like too much time to kind of explore that. But like if you're interested, come talk to me. Yeah, and then my office hours, yeah, happy to answer your questions there. And yeah, I hope you don't have too many questions and everything kind of works out of the box, but it's robotics, so there will be some questions.
All right. Thank you, Marius. Next up, Karthikeya.
I'm Karthikeya. I'm a BSMS student in computer science. And yeah, those run lab hours, they'll always be in the CSE1 basement lab, O22, where we have all of our projects. And yeah, for my robotics experience for the past year, I've been working with Abhishek in his lab, working on like compliant or soft robotics. Before that, I was working on like updating robots, using like feedback. And yeah, before college, I used to do FIRST robotics. I don't know if any of you know what that is, but
Cool. Thank you, Karthik. Inchu?
Hi, everyone. First year teaching student for one by occupancy. And I'm using combining traditional control method and learning together to make the phone smart. Before joining UW, I'm from CMU. I did master here. Yeah, my hours over is on Monday and Thursday. Want to all here.
Thank you, Inchu. Enough, guys.
Hi, everyone. I'm Bernard, I'm a master's student. I've been doing robotics research in CSE Robotics lab, mostly in multi-agent systems with emission cars. I guess no one else put a fun fact, but I put the notes for cereal. So if anyone wants to know the right way to do it, I'm more than happy to teach you.
All right. I think our class is small enough that we can do quick names and, you know, one fun thing that you want to get from this class, maybe, right? Names and, maybe year you're in CSE, and one fun thing you want to learn from this class, right? Let's see if we can get through it. Because I do want to learn all of your names, so. Yeah, sorry.
Yeah, I'm Ashley, and I am a third-year student. And I guess from this class, I want to learn more like specific intricacies in programming robots, because I brush the surface a lot and both first robotics and robotics capstone. But I want to get more into the depths of kind of like start from scratch or something like that.
Okay,
Hi, I'm Raymond. Should I just follow the format over there?
that seems great.
Math and CS major, hometown in Covington down south, about an hour away. This is my second year here, and I really wanted to learn more about the ROS software,
Cool.
along with machine learning methods and robotics. Something about myself. Hopefully, I go to the gym this year.
Me too, man. Me too. Got it.
Okay, so my name is Leo. I'm a CS major. I'm from Issaquah. I'm a second year, and the part I was interested about this course is that I'm interested in like reinforcement learning for robotics, but you said it doesn't work.
But that's great for research. Yeah,
Yeah,
it's good.
and thinking about myself, I'm almost one.
Oh, well, okay, cool. You don't have to if you don't want to. Ah, nice. Very cool. Good.
I'm Yoga. Yes, I'm a student. I'm from Spanish. Did a little bit of robotics.
Oh, that's good. Thank you.
Hi, my name is Sasha. I'm a junior in CS. I'm also from Redmond. This is my third year. I said that I wanted to take this class because I just wanted to, I guess, learn something different from what I've done before. And then something about myself is that I really like experiments.
Kevin, graduating in June. I grew up watching BattleBots, so I'm pretty like
Nice.
build a car. I didn't really know what this course would entail, so that's excited for
It's
that.
only $1,000, yeah. We could battle bots a little bit.
I'm Daniel. I'm a senior in CS. I grew up in Spokane. I took this course because it sounded cool, and thankfully it still sounds cool. I'm learning Japanese.
Oh, very cool. Fair enough.
I'm Kaden. I'm from Bellevue. Yeah, It's my third year. I'm taking this course because also it sounds very cool. I'm not, don't really have any robotics experience, but I just finished my internship at Tesla and it's a lot of nice robots.
Yeah, very cool. Nice. Yeah, but-
But also I'm into running.
Ah, cool.
Hi, it's Nate. I'm in CS Economics, Bellevue, second year job. I took this course. I want to learn how to use the linear quadratic regulator. I've used it in high school. Failed. We just switched back to PID. I've been doing robotics for like a while now. I started doing first robotics in like fourth grade. I'm on the advanced robotics team here.
Hi, Michael. Very good. It's hot, dude, that's all.
And it is.
Hi everyone, my name is Jaden, I use they pronouns, I'm a CS and music theory major. My hometown is in Issaquah, I'm a senior. I took this course because I am an officer on a robotics team, but we actually don't do anything autonomous right now, so I
Okay.
figured I probably want that knowledge. And also when I was a freshman on this team, we used ROS, and then we entirely scrapped the ROS system in our software, so I figured I might go back
Okay.
and figure out what it was supposed to be.
Very cool. Go ahead.
I'm taking this course process, and also I'm curious about how that's the velocity of the stuff. Innovation versus covered, but I'm still interested in.
We'll cover it a little bit.
I am now, I'm a senior in computer science. I'm interested in taking this class because like, I want to learn like how the control system work. And I'm into sim racing.
I guess you. Okay.
Yeah, I'm Gash, I'm from Woodview Island, and I'm a senior here right now. Yeah, I guess from this course, I really want to like learn like motion planning, maybe some
Okay.
stuff. I mean,
Very cool.
this looks like
We'll cover a lot of motion planning, but we will cover a little bit of SLAM.
yeah, I guess like a fun fact about myself is I'm terrible about I'm terrible at coming fun facts on the spot.
Okay, nice. Good.
Hello, I'm Johnny. I'm a third year CS major. And I'm taking this class because I want to learn more about autonomous robotics. So I low-key came in expecting some computer vision stuff, but
Maybe we'll cover a little bit, but not a lot. Yeah. Talk to Marius. You'll have a lot to say. Let's see.
Yeah, hi, I'm Joel, and it's my third job, and I'm super interested in global learning and robotics, and that's why I thought of CS.
Awesome.
I'm also doing control in EE, and I'm a former member of Arizona, and yeah, I guess it's about the job.
Cool.
Hi, I'm Jake. I'm a CS major from Seattle. My last year at UW, or it's my last quarter actually, so hoping to take some really cool courses. Last one, haven't done any robotics really or much with hardware. Class with me.
Yeah. Cool. Thanks. Cool. Thank you.
Hello, my name is Robin, and I'm a junior in computer science. I took this class because I want to get into research in politics, like reinforcement.
Nice.
And yeah.
Cool. Thank you.
Hi, my name is Robin. I'm actually one interesting thing about this is my second master is the industry.
really interesting to approach that getting platform.
Yeah.
Brain is being already established and can.
Right.
So how much we
Cool. Right. Thank you.
So my name's Adrian, I'm third year computer science in Rutgers. I think I'm just generally interested in robotics and I thought to be a Thomas program.
Thank you. Right.
Hey, my name is Sammy. I am also a third year computer science major from Bellevue. And I guess I've always been kind of interested in autonomous vehicles. And at a top level, I've understood how, like, I guess systems work together with robotic software, but really underneath, I don't really know anything about that. So that's why I decided to take this course. And something about myself is that I also put
Nice. There you go.
Hi, I'm third year in CS and ACNS. I just want to learn more about applications of ML and then probably dive into CD or research. So one fun thing is that in the past quarter for deep learning, me and my friend were running a simulation for autonomous driving. And now for language model, and we're actually trying to see.
Very cool. Okay.
Hi, I'm Daniel, third year CS major from Bellevue. Taking this course because I never saw it on the course title before.
Oh, cool. Nice.
I don't know much about robotics and stuff like that.
You will soon, yeah. Cool.
Fun fact,
Can I go? All the way at the back, yeah.
It sounds in this course because of the higher experience in robotics, I'm going to this field. Fun fact about me, I am a
Thank you. Right. Thank you. Thank you. Bye. Good. Thank you. Bye.
Chad, computer science, Harvard, second year. I thought it'd be fun. Making videos of stuff. But
Cool. All right. Thank you. I think that's everyone. Did I miss anyone? Great. Cool. So let me, I will remember everyone's name by the end of the quarter. If I don't, call me out, no problem. But let's talk about, course logistics, so you know what to expect. Roughly the grading we're going to do is we're going to have 4 programming assignments, right? So each of these programming assignments cover one aspect that we talked about. The first is going to be just an introduction, and then we're going to have one on localization, one on planning, one on control, and then a final project that puts them together. And for a more accurate grading rubric, you can go on the website. It's at the bottom of the website, but roughly it's like a 4th per programming project. We're going to have some amount of grading on paper review. So we're going to have 4 paper reading sessions where one of our groups is going to present a paper. And, you have to present, what is the background, what is the key insight, what are interesting things about the paper, what are critiques, what could you do better, and we'll coach you guys through how to do that. But each team has to do one paper review, and we expect you to do commentary on each of the paper readings that are provided. So you just need to provide commentary on EdSTEM, a couple of paragraphs describing what you learned from the paper, new insights, new ideas that you got from it. And that's going to be some portion of your grade. Then you have a final project, which is putting together programming assignments 1 to 4, trying to, optimize performance, take it to a new environment, so on, right? And so, that's where you can be creative with what you do. And lastly, there's some participation. It's lonely if I'm here alone, so please come to lecture. We'll have some guest lectures. It kind of sucks if they don't have people in class. So please come to class. I don't take grading too seriously. You'll probably get a good grade. Don't worry about it. But the hope is that you learn something from this class. You can program some robots, and a lot of you, take robotics way more seriously after. So don't worry too much, but really a bulk of the class is based on these programming assignments. And so we have these 4 different assignments. They're all on the website already, so you can take a look. Not everything is fully set up. We'll have it set up by tonight or tomorrow. Post an announcement on EdSTEM when they are. Right, but the first is just an introduction to get you used to ROS, get you used to the programming framework, get you used to the cars. And then we have a project on localization, project on control, and project on plan, right? And they're pretty well documented. There'll be an element of them which is in simulation, an element of them which is in the real world, right? And so you'll be graded on both, right? And so we're going to do this in teams. You're not going to do it alone. We'll have teams of 4, right? And we'll assign those teams shortly. But you have teams of 4, you can do all these assignments. There's auto grading, no hidden grades. You just need to get it, pass the test. So roughly the organization of the class is going to be, we start with an introduction, we cover state estimation and localization. And that's going to be project 1 is just an introduction, project 2 is about localization. We'll then cover control, right? And then we'll have project 3, which is on control, and then we'll cover planning. Project 4 is on planning, and then we have learning, reinforcement learning, special topics. No special project on that, but we'll have the final project. Right? The way we're going to assign teams is we're going to be assigning them by the staff so that we can balance people with more experience and less experience and try to keep all the teams roughly equal. So we have this knowledge survey that we've put up on the website. I think it should be accessible now. So if everyone can fill out the knowledge survey, then we can balance teams out appropriately. There's going to be teams of 4, except for some of them might be teams of 5, depending on how many we have in the class. But try to fill it out by today or tomorrow so that we can assign teams, because once you assign teams, then you can go pick up your hardware and get started with the class, right? So please fill these out. If not, I'll have to email you to bother you. So please do so quickly. We'll have the same team for all 4 projects in the final project. If you have a problem with your team, let us know early so we can change it. Right? Hopefully that's not the case, but just let us know and we'll make everything work. Right? All right. Generally, pro tip is that simulation is way easier. It often works a lot quicker, and issues that you have will show up in the real robot. Often robots have lots of tinkering that you need. Our TAs will help you with a lot of it, right? But it's useful to budget a lot more time for the real robot experiments than the sim experiments, right? And so generally with robot assignments, you don't want to start it on the last day. It's not going to work. So start it a bit early, life will be easier, right? We're going to grade most of them on satisfactory, unsatisfactory. But each project builds on the next. So you really want to complete each project. Otherwise, your next project's not going to work. And so if you don't complete it in time, we'll give you feedback. You can resubmit, right? So the hope is that you can keep building on things, and we'll help you out with things. To help you out with things, we're going to have office hours. So lectures are Monday, Wednesday, Friday. I stay back after lecture for a while to talk about things. But I have extra office hours on Monday and Wednesday, right? So please drop by if you want to chat about conceptual questions, or chat about research or about homework, although I think the TAs will know better than me. And then we have lots of TA office hours, right? So these are all going to be in the lab. So in the Allen School, 022, which is the basement. You should all have access to it if you're registered in the course. If you don't have access, email me or post on EdSTEM and we'll fix that, right? But there's lots of different office hours. In general, you can come into the lab and do experiments whenever you want. But if you want the TAs to help out, those are the times to do it, right? And before the due date, you want to like come to one of the TA office hours and run your homework for the TAs to just mark you off. And otherwise you can use the resources whenever you want. Just don't steal the cars, you know. You can ask questions asynchronously through EdSTEM. We should be pretty responsive about any conceptual or homework questions you have. Most of you should have access to it. If you don't, let us know. In O22, you have 10 cars, I believe, right? 10 cars. Each one of you will be assigned one car for the quarter. You also get a dedicated workstation, right? So each team will have a workstation, plus there are some miscellaneous workstations, right, folks? Yeah, so each team has one workstation. There's some miscellaneous workstations. You can log in with your UW credentials. They have Ubuntu, Python, and ROS pre-installed, so they should really be set up for you guys to start, doing things on them. There's also an option to do things on a VM, but you want to be on the workstations to do things with the hardware. Right? And so you each get one dedicated race car per team. Right? Keep the same race car for the duration of the class. Don't take other people's race cars and batteries and parts. Because of the first week and we have some folks still out, we have 2 special office hours so that you can come pick up your cars, make sure everything works on Friday from 10 to 11 and 3 to 4. So just one of those times you and your team should come in, make sure that the car works. The TAs will be there. They can help you get set up and on your way. Yeah. I'll email everyone your team is signing or by latest Friday morning, because it depends. So yeah, if you don't fill it out, then the teams will get delayed, and everyone will get delayed. So you should fill it out. And so, yeah. So generally, the cars are pretty robust, but treat them with respect. Please don't battle box them. Don't change the password on the cars. We've set them up so that the networking and stuff is not a pain. Each team is given a bunch of batteries and you have chargers. Maintain your own batteries. And don't make a mess of the space because everyone's sharing the same space. And yeah, don't take the cars home. Bad things happen. Just leave them there. You can work in the hallways. You can work in the room, but just want to keep them. And just don't cheat. It makes life hard for me. So yeah, the standard policy. The policy is on the website. And I think we might be out of time. But next class, I'll show you guys a bunch of cool robot videos. Okay, thank you.
We went through like stitching issues and all of that. They also need to work out, so we're ready. That's what batteries are good. Ready? Okay. For our last one.